All right, it is time to start the broadcast. So we're going to go ahead and get to it. We'll let everybody else log in as they arrive. So thank you very much for joining us this afternoon here on the East Coast, still the morning, the rest of the United States. My name is Darin, and today we're going to be presenting designing with 3D printing in mind. Now, some of you have met me before. I've been around for quite a while, and you may know my affinity for 3D printers. Being in this business for as long as I've been, I'm not here because I don't enjoy myself. So I spend a lot of time outside of work actually using SolidWorks and of course, my 3D printer. Now, a lot of times dealing with my toys. As an engineer, I like toys. I'm sure a lot of you are pretty much the same way. So my drone is one of my favorite toys these days. But basically, I spend a lot of time when I'm not here at the office doing things on my own and stretching my legs with SolidWorks and really using it for the tool it's meant to be used in commercial environments. And that's just for testing an idea and making sure that you're right on track before you move forward. So whether it's using weldments for things like my treehouse here, or whether it's mocking up a basement bathroom just to make sure things are going to fit before I start putting things up on the walls, it's important to use the CAD tools to your advantage, and knowing the end game is the most important part of that, of course. Now, I have a 3D printer, and the 3D printer is one of those things where it feels like a toy in some cases, but it really depends on the way that you use it. And obviously, these are being used incredibly effectively out in industry. And what that allows us to do is build things in a much shorter time frame, of course, and deal with things that are unmanufacturable in traditional methods. Now on screen here is a part that I invented a couple of summers ago, and turned out to be one of those situations where the part in the upper right actually was my first iteration and turned out to be a complete failure. And that cost me about 3 hours of my 3D printer and 700 grams of material. In this particular case, pretty small part, but in this case, this is one of the situations we use to test out a product. And once we can flush out that design using 3D printing, that gives us confidence moving forward with high scale production, or in my case, a usable end good. My latest adventure was tearing apart a trolling motor and tearing out the guts and getting rid of most of it and designing up a nice little body here to encompass the mechanism for speeds, forward and reverse. And that enabled me to go ahead and print the finished product that now sits on my boat and frankly looks like it's meant to be there. So we can use 3D printers for a whole lot of things, but my favorite purpose really is for creating end products or final use goods. Now, we have a YouTube channel at DASI Solutions. We try to put as much knowledge as we can out in video and try to get it out to you. So if you would go ahead and just visit YouTube and just search for DASI Solutions, you'll be able to go ahead and join our page. So I'm creating content as much as possible, and there's a lot of other techs at DASI Solutions creating other webinars and tips and tricks and different topics as well. So please go ahead and visit the page, and that's just going to grow our subscriber base and get more and more videos produced for you. So this is our agenda for today. What I first want to do is cover some basic print methods. Now, unless you're absolutely new to 3D printing, I doubt you're going to learn something mystical or amazing today. But really, these are the things that I have to keep in mind when I'm really producing a part that I know I'm going to 3D print. And really knowing what kind of printers are out there and what they do is one of the most important parts of it. Now, we're forced to go in a particular order here just simply because of the way we have to present, but I really do feel that many of these, if not all of them, have to be taken into consideration at the same time when really choosing how we're going to proceed. But of course, the way a printer works and the type of methodology it uses is a real key to this, so you've got to understand that. And then we'll get into a little bit of really discovering what we're going to use it for and how that's going to drive our decisions, size being one of those things. After that, we're going to move over into SolidWorks and get into a few things here, like the chocolate Easter bunny. That's really a big consideration when it comes into the 3D print method as well. Do I have your support? Every print method has support structure of some sort, and it has implications into exactly how you proceed with a design, and really how you go ahead and format and position your printer when you're choosing the right direction for it to lay in the print medium. Fillets are your friend. Now, we'll talk about that at length, but it's one of those things where in a CAD system, we many times tell you not to use fillets, and really that's more of a performance benefit for your video card. But as far as 3D printing goes, even parts that don't have fillets can really benefit from what they do. Lastly, after talking to our support technicians here at DASI Solutions, I got a punch list of a couple of the things that would really help them do their job for you better when you do have your parts outsourced to us. So first, let's start off with 3D printing methods. Now we have a big list of things here, and I'm not even listing things like binder jetting and some other methods that have just become new. But these are really the main ones, and I can boil it down to 4 types that really cover the gamut of what we're talking about here. Now, if you go to Google and search for 3D printed or 3D printing, a lot of different things come up. And it's not even as much as the method that we use to print, but also the final product or the medium that's used. It could be something that's plastic, like we've shown before. What we see here is actually sugar cubes. It's more of a binder jet method where we put the binder into a vat of powdered sugar, and then it simply binds where the resin hits. And it's an edible form so that we can create these types of end-use goods. But again, having the end use in mind is a big deal here. But there are definitely as many uses for 3D printers as there are types of 3D printers. So we'll start with FDM, which is really the most common. We really refer to this a lot of times as a hot glue gun on steroids. You basically have your heater heads. They've got a tip to them that's a particular size, which speaks to the resolution of the machine. And sometimes, most cases, the cheaper models here have a single tip, but the ones that have either multi-materials or a separate type of material that's used for the support material would have a dual extruder. Now, these are typically quite accurate types of printers. Not quite as accurate as some, but they do have quite a good resolution. But they're quite quick and usually less expensive, both to maintain as well as the materials that we use in them. So again, this is usually more of a 2D print layered on top of each other, and you're going to see the different layers in the final product quite evident. And again, that's all speaking to the quality of the machine. But essentially, it's a series of 2D prints layered on top of each other. Now, it uses a gantry system. Some use a triple robotic arm that also moves the print head around. But whether you're moving the bed, moving the print head, or a combination of the two, it's a pretty common method out there, and many, many printers available at many price ranges. Now, with something like this, if you just simply scale it up but use similar methods, then you end up with a contraption like you see here. Now, this is more of an FDM or a fused deposition, but it's using mortar instead of plastic and a large robot to distribute. So same method, different application or different medium. So the ingenuity of users out there is great, where they can take one application and simply dovetail or pivot from there and create a similar but almost completely different application all at the same time. In this case, upscaling it for commercial purposes, we can print houses using this device here in just a matter of a couple of days. Now, FDM typically takes post-processing, whether that happens to be dissolvable supports like a Fortis type machine would use, that requires some support materials and machinery for that as well. The less expensive units are typically breakaway support. Now, whether that support is a completely separate material or it's the material that's just used in a little bit finer spacing that's used for the normal part, you're consuming materials either way. Now, in my case, I have a breakaway support machine, but I'm really just a fan of supports in any event, because machines without support capabilities are far less capable of creating sophisticated geometry. It really does limit the way a part has to be designed and positioned in the machine. So anything with supports is a plus. Dissolvable supports usually yields better surface quality than breakaway. Now, Polyjet is actually more of a photosensitive polymer. And it's a lot like the way that we get fillings in our teeth these days. They put a little bit of the polymer in your tooth, and then they put a nice ultraviolet wand in there to solidify the plastic or the resin. And it's the same way that our Polyjet machines work. It'll lay down a layer of this photosensitive resin, and then it will hit it with a UV light on another pass that will cure that resin. And it's progressively curing about 3 layers at a time at different progressions to promote the adhesion from one layer to another. Now, these are also multi-material machines where they can have a combination of black, white, clear, and some black can be either rigid or rubbery. So as we mix these different layers in different durometers or different ratios, we can get different durometers and or grayscales of material. Now, this Connex machine also has a derivative that has full color capabilities, which will get you 16.7 million colors and add a real tremendous amount of realism to the final product. This too requires post-processing, but it's generally just using a water jet of sorts or a water pick to get rid of the support structure, which is more of a wax-based type gel. So it's pretty easy. The surface quality is quite good right off of the machine, and based on the position, you'll get either a matte finish side or a glossy side, depending on what touches the support material. Now, carbon fiber infused, as well as metal printers, are really becoming more and more popular and less expensive as a result of their popularity these days. When you're dealing with carbon fiber printers, these are adding layers based on a bit of a vetting or simulation that their software does. And based on the way the part's going to be used, it will strategically layer the strands of carbon fiber between the layers of more traditional FDM type printing. So it's a fantastic tool. Now it creates very good end-use products. It can shrink the size due to the improved strength, or it can just create an unmanufacturable but strength necessary type of a part that can be used just simply as the end product. Really great example of a nice ball joint here. Now this is a part of a bicycle, and this is what I consider really to be a mission critical type of a part. When I was young, I had a friend that actually had this part fail on them as they were pedaling very hard and standing up, and as a result they had a pretty traumatic type of an experience with an accident, and really don't ride bikes to this day because of that. So trying to put a 3D printed part through its paces in this application, to me, really does speak to the quality and the strength of those products. Now, metal is really where the industry is going to be revolutionized, and it's going to come down to the way that these parts print, their speed, and the ability to use them even up in the highest applications like turbine motors. Essentially, you're printing them in traditional methods, but we print it with a little bit of a powder-bound plastic, and the plastic has metal built into it. So the software builds the part larger or smaller as necessary so that when the plastic is obliterated during the sintering process, it will equalize to the proper dimensions that the part was designed to. Now, it leaves you with a part that's 99.7% dense, and that's very important because traditional selective laser sinterings usually leave a part that's quite pitted and therefore is not strong enough for those very dynamic or heavy applications. So this is where metal is going to go to the point where it's going to be cohesive enough to be just as good as a manufactured part from some top quality alloys. Great end-use parts that we have here as well. So impellers and other types of mission critical parts. Now, as of late, I've become a little bit more familiar with continuous liquid interface, and it's a pretty amazing thing. It works in reverse as opposed to a lot of the other things that build on top. This is actually building from underneath, and what it does is it uses a projector, and much like a traditional stereolithography method, it's solidifying a layer underneath in this oxygen permeable window that they show, and then from there the part rises up out of the resin. Now, you can build some tremendous things with this. The one on the left is pretty amazing, but the one on the right is actually a pretty dynamic type of a material. Not only does the lattice work really in incredible shape, but it allows you to create very organic shapes using these types of tools in ways that no other types of printers would be available to do. Now, these organic structures really come from other types of design methods that we'll talk about a little bit later. But what it's going to do is what really determines a lot of what we see right now. Now, if these being shoes, of course, they're going to have to be flexible. So we need something that's going to be a more rubberized type of material as opposed to rigid. The shoes that you're seeing here really don't look a whole lot different than the Adidas that I'm wearing right now. The soles on these shoes are what you saw coming out of that continuous liquid interface production machine. Now, I haven't looked deeply into the cost of these machines. I'm sure it's quite significant based on the end result and the fact that this shoe's printed sole is on a pair of shoes that you can have for the low, low price of $132 a month. So I think that right there tells you that this is a long ways off from being an affordable type of a method. But like DVD players were $700 when they came out, and they're $20 now, the price of this will go down as the proliferation of this technology does get out there. Now, I'm more familiar with these two types, the Connex Polyjet method, which we use for parts that we need to either have some rubber in them, some nice clarity to them, or just need to be a nice, really good quality surface. Or my Fortis machine, which gives me very rigid, very strong parts off of my FDM quickly and very inexpensive. So let's talk about these. You have to consider what's good and bad about each of these. And in a lot of cases, what we're talking about is strength versus accuracy. Surface finish on Polyjet is much better, but on FDM, you're going to have a lot more strength as a result of the worse surface finish. So brittle plastic over here, more expensive, and there's a lot more support hardware to support a Polyjet machine when it comes to things like the water tank that you need to be able to go ahead and high pressure wash your parts. FDM being considered when it comes to dissolvables, you still have a lot of support hardware for those as well, but in most cases you can get inexpensive FDM machines just on Amazon or eBay these days. Metal, very expensive for all of us right now, so that's going to be outside most price ranges. Although with Mark Forged, they are bringing this down significantly with their machines to about $85,000 for a metal printer, which these days is pretty affordable. All right, so size is key. Now, when we talk about size, this is the first part of this demonstration that I want to get into, and we really have to consider what we need versus what we want, and that really is a question with everything that we do with this presentation. So with what we need versus what we want, what we're having to consider are things like, does the part need to be printed full scale? Now, if it does need to be printed full scale, well, of course, yes or no. Well, if no is the answer, then you've got a lot of options. Sometimes the 3D print is more for a visual than to actually have a physical fit part size. So if you're just trying to get a look at a part, maybe curvature, something that looks appealing under light, maybe you just print it based on the printer that you have available. However, if the part does need to be printed full size, now we have to make another decision. Well, do you have access to a printer that can print at that size? Because everything does have a build chamber, and that's going to be a main constraint when it comes to the choice of your printer. Now, in this case, if you do have a printer, great, set obviously, but if you don't, we've got to do one more thing. And that's where what you do in the CAD product can actually help you. So in this case, we're going to go into SolidWorks, and we're going to deal with this little feature that we have called a split part, and an example for a file that I had to deal with recently. So jumping over to SolidWorks here for a minute. This is the rudder to my pontoon boat, and I'm sure you've seen this if you looked at my videos or even some of the pre-stuff that I had here. So not a very exotic model, but one of the things I had to do with it is I had to go ahead and produce something that gave me more turn. It didn't have enough angle, so what I tried to produce was a part that I attached to it that effectively gave me more throw. So more angle to the right or to the left when I would throw the rudder in both directions. And then I reversed the process in order to have that work as I backed up, not just as I moved forward. Well, that being the case, this is a part here which is significantly larger than my 3D printer capabilities. In fact, the full length of this particular part is about 18 inches. Now, in order to go ahead and deal with that, I use a simple feature inside of SolidWorks called split line. Now, split line is one of the items you can do, but you can also go ahead and just say simply insert, go down to features, and do this thing down here called split as well. Now, this requires a sketch. So with a part like this, it might just be picking on the top face and starting a new sketch. And for something like this, I actually like to go just a little bit more exotic, just so I have a part that's going to fit. So it might be something like a line that does this, gives me a little notch for seating purposes, and then maybe it looks like that. That's all pretty good. So when we go ahead and actually do the split feature, say insert features split once again. And what this is going to do for us is actually take our sketch and chop us up into two separate bodies. Now those bodies can then be printed individually. So if we just simply do a move copy bodies, I'll take this part over here and slide it away. You can see that what we now have are two separate individual components. And that enables me to print them both within my print constraints and then assemble them later with cyanoacrylate or any other type of binding material that works for the material that you have chosen. Real simple thing though. That works for any part, frankly. And sometimes design actually predicates that when you're dealing with consumer goods where the top and bottom half of a device need to fit together. We would design them in that respect and then do a multi-body or a split part type of a design approach. But in my case, really is just a simple way to go ahead and build a part that's going to print and then assemble them after the fact. Another way that we can take a very small printer and effectively print an entire engine block or head, which is really more large, much more large than a print could handle. So let's move on to the chocolate bunny. This is a term that might be kind of funny to everybody, but you might have also picked up on it as well if you're not new to 3D printing. The chocolate bunny really refers to, is your part hollow or does your part need to be solid? Now, hollow and solid are somewhat arbitrary terms when we're talking about 3D printing, and I'll discuss why that is. But when we're looking in SolidWorks specifically at the CAD file, mass properties and hollow or solid are taken very literally. What I have here are two brackets, and these happen to be pivot arms for a hinge mechanism. Now on the left-hand side, I have a defeatured version of this, and on the right-hand side, I have a feature that's got some pockets all the way through and then some pockets that are blind, but effectively a much smaller mass area to the part. Now if we make the part out of the same material, give it a density of ASI 1020 steel, having an equal density and different volumes, of course, are going to lead to, in the CAD system, very different mass. In this case, volume obviously is going to be literal on screen, and we've got a part on the left-hand side which is 33% heavier than the part on the right. This is a foundation feature of a CAD system. But when we 3D print these parts, that's not really what we're getting. What I have is the part on the left, which is the full part, not pocketed out. And if you look at this versus the part on the right on my gram scale here, you'll notice that the one on the left is 24 grams, and the one on the right, 33% smaller, is only 23 grams. Now, obviously, there's not a big enough resolution to see more difference than that, than a full 24 grams. It tells us right away that there's absolutely a difference between a 3D printed part and a traditionally fabricated part out of something like metal or wood. When you look at a part like this, we're talking about the hollow, the Easter Bunny. And what I did here is I actually took the part on the left-hand side and just did a shelled out the backside. And in this case, of course, we've taken a tremendous amount of the material away from the part. And as a result of that, what we now have is a big mass difference. But when you 3D print it, this isn't the cross-section that you actually get through those parts. When you 3D print the part on the left-hand side, which cross-section is solid, this is what you get. You get a wall thickness, both vertical wall thicknesses and horizontal wall thicknesses, and all of those can be determined inside of your print settings. Now on the right-hand side, this one is a hollow part, but this is what you 3D print. And when you look at the two, your eyes tell you very quickly that there's actually more material over on the left-hand side when it comes to wall thickness because of the duplication that we have to do with this thickness. Now the hollow area here, I didn't bother to model this, but that's where the honeycomb comes into place. And I'll talk about this in just a minute when I go back over to the webcam. But this is the difference, is what your percent fill is identical on the two of those, but when you have a part that you've hollowed out in SolidWorks, that might not really be what the result of the material is being utilized through the 3D printer, because of the way that it builds inside and outside walls and hollows the rest of the cavity for you. So we're going to talk about support structure, and then I'm going to move back over to the webcam for just a second here, because support structure is just as critical, and each of these types of printers has a different method. This is an older printer that we used to deal with here. It's a Z-Corp machine. That uses a potato starch and does that binder jetting. So a Hewlett-Packard print head, if you will, shooting a liquid binder into this vat. As a result of the method, because of the fact that you're hitting layer after layer of powder and you're only hitting a portion of that with binder, the powder itself becomes the support mechanism. And in the end, you shake the powder off and then you have your finished part. Maybe you wash that as well. The Connex machine, significantly different, but very similar. In this case, we have a completely different material for support. We have a harder material, the resin, for the part itself. And here where you see the yellow banana colored stuff, that's more of a wax-based support material. So in this particular case, the support material is going to only be below the part towards where it hits the build platform, or interior to the part if there happens to be any overhangs or ledges, like these interior tabs on the inside of the part. The other thing that we have to really think about with this, and we'll talk about this a little bit later as well, is what faces are touched by the actual support in this case. So flipping the part to the proper position. Now we also have to think about that when we're dealing with fused deposition. Now in that case, there's a few other things to worry about. And again, we'll talk about those in a second when it comes to position and orientation. But where that particular support mechanism has to hit the part is going to change the surface quality of that face. So we want to put that in the proper position. But when you're completely immersing the part in support position, you don't have to consider the same types of things as you do when you're building the support proactively. And that's going to be things like overhangs and ledges as well. So in the case that we're talking about these FDM parts here, so the stuff that I have here on my 3D Wax machine, we're talking about the angles and the overhangs quite significantly. So let me jump back over to the webcam here for 1 second. And what I want to do for you here is just go ahead and show you some of the parts that I've got on the table. Okay. So what we've got right now is a series of parts here, and some of these I went ahead and took the support material off of, and some of them I haven't. So this is an impeller that we printed up for a lake pump. Happened to break, and we just built up a part that is now the end-use part directly inside of that lake pump. A couple of other parts that we've got here you've seen on the screen. This is a little bracket for an optical focusing mechanism. And when you talk about a couple of different things here, we'll talk about overhang first. With my particular printer, 45 degrees seems to be the angle of criticality when it comes to whether it's going to build overhang or not. Now, with the part that I've got over here, this one I've left the support material on. So you can see that I've got one that's actually hanging out here in space. But when we look over at the side of the part right over here, anything that had 45 actually did not get any type of support material printed. So there's always an angle based on the method. And again, FDM is something you've got to be a little bit more critically aware of in those cases. The other thing I talked about here was the chocolate bunny. And this is a base that I stopped partway through the print. And this print happened to be for a catapult mechanism. So it's a very big and bulky part, but the reality of it is the interior happens to be made of whatever percentage fill that you deem during your print settings. So this particular case, of course, we're talking about the actual honeycomb on the inside. And various percentages are usable for this, but do it as strong as you need to, but not to waste material building up a part like this. So those are the key things. 45 degrees happens to be something that's a pretty common thing, but other printers are going to have different capabilities just based on their setup. And the CUDA processor, Cura processor, software might work different than my 3D Wax software does. So back over to the computer for 1 second here. One of the things I want to show you on this is how your computer is going to let you know what's happening up front to these kinds of things. So with this particular part right here, I want to get into a component that I ended up printing as well. Again, just to show you exactly what your computer is going to see. So a part like this can be printed. Now, a lot of times this is something that you'll save as an STL file and then pull into something like Makerware or the Connex software or some sort of pre-processing software. In SolidWorks, you can actually go to File and say Print 3D if you have a 3D printer that has a standard Windows driver. And it'll actually go ahead and work through over here in the Property Manager the different types of settings that you would do for layer heights and speeds and feeds and materials and so on. You do have to have that Windows printer, which is available for a lot of the hobby level printers that are out there. My particular printer actually has software that works inside of SolidWorks. So when you take a look at the tab here, you can really just go directly to Print 3D, and it will change the interface and give you all the details that you need about position and how much material that you're going to use in a part like this. Now I happen to have pink loaded up. I was printing some jewelry holders for my daughter last night, so that's what we've got in there. And in the support software, you have choices for everything. So what your quality and infill is going to be, and 15% is pretty common here for when it comes to the type of honeycomb that you're going to see. What I'm going to deal with on this one is going to be more of the support mechanism to it, though. So right down here. Now, when we go ahead and say that we want it either touching the build plate or everywhere, it's going to show us on screen what this is going to look like. Now, before I actually do this, my tool also gives me some optimization capabilities for the position of this part, which was built on end based on the front, top, and right planes. And when you analyze these, it's going to move it into a position that's going to be best for form and fit and usability. And a lot of times it'll be, looking at thin regions and layer thickness and position, as well as support mechanism or support structure position. Oh, excuse me, I got to take that one. So when we go ahead and actually run this, the one in the upper right here, I'm going to go ahead and select, and then that will move my part into that position. That said, when you go ahead and take the fact that we do want supports set up and you preview this, any of your slicing software is going to give you visuals as exactly what faces are going to be touched by this support. And that's going to tell you again up front exactly what faces are going to be marred by that support in some cases. So here we have a part which is sitting in a vertical position, and all the blue underneath is my support. And you can even take a look at these and simply go through by layer. So if we go ahead and just simply slice down through the part, you'll even get a very good visual as to exactly where that honeycomb is going to be built, right here, the green on the inside, versus red and yellow faces, which are inside and outside faces of what is a hollow walled part. And then again, you can see where that support is going to be created, all of the blue there. So that uses a lot less material, but it has to create a raft so that when these faces are built up in the middle of space, it has something to actually extrude the plastic directly onto instead of just oozing out and creating effectively a purging at that point. So this is really what you want to look at when it comes to what your software is going to tell you about the products or the parts that you're looking at. Now I showed you this a little bit with the hand puppets on screen, but let me just go ahead, because we do have some time here, to go ahead and show you this in SolidWorks as well. This is the bracket that I have several prints. And when you go ahead and do the same types of settings here, because of these drastic angles, we'll deal with some support on these as well. Do everywhere. And then when we preview this, based on my print and my position, it's going to build that support wherever necessary. And in a lot of cases, again, you can get away with not having support out on these big faces simply because the layers overlap enough to the previous layer in order to have support previously built. It doesn't need that built right out here in space. If you make layers that are going to be a lot more coarse, that might actually trigger some support material being built out here because there isn't enough overlap for those ledges to be built or produced properly. Now the part that I'm building here, this is really a poor example of how I would do this, because the way the part is sitting is really in the bad position as far as how much support material I'm going to need. So a part like this, if we analyzed it, in fact, this part was actually built in print position to begin with, this is the best way for a part like this to actually sit on screen. So that way when we print it, we'll have a minimal amount of support, which means a minimal amount of wasted material being used in SOLIDWORKS as well. Now we just need blue supports inside the holes, but really only just for the one overhang and the flat horizontal face on the edge. So that's what you want to consider most when we're dealing with this. It'll show you based on your thicknesses exactly how long this part should print and exactly how much material is going to be consumed by the combination of wall thicknesses and infill percentages. So I really baked this into the previous discussion, but it's the orientation for your print. And what happens with the orientation for the print really does affect the cosmetic nature of it. So one of the previous thoughts or constraints is, what's the end? Well, is the end going to be for pretty, or is the end going to be for use? So you want to make sure that if it's just for cosmetic purposes, that we choose the right printer, which would be more of a Polyjet type of a printer, but that we also orient the part in the machine so that the matte face, the matte finish, is going to be touching the support materials, where the gloss finish would actually be pointing upward. Now, in a part like this, that's going to be something where the material that we use here is approximately a 3-to-1 ratio in expense. So more support material in this case isn't really a problem. It's when you print too much of the actual resins that becomes prohibitive. When we deal with FDM, layered direction happens to be everything when it comes to strength. If you make a very long part and you orient the part in the material, the layers of the lines in the orientation that I consider to be more of the karate kick type position, if you will, the grains are in a position where they will collapse quite easily. And if we do them in length, then that's going to be strong in that orientation. Really is all just about strength of materials and the orientation of the laminate in that case. Metal is really kind of out there still. I'm not quite sure what to say about metal yet, because in reality, metal prints very much like both of these. There's support material being printed there, so very much FDM based. It's printing layer by layer as it stacks up, and then there's pre or post-processing that has to happen to a part like this as well. So orientation on this one, it's using similar materials for both of those. So I really think that the strength drives orientation more than finish in parts like this. And I didn't really talk about carbon fiber, but carbon fiber printers, 100% the orientation of those strands is going to be based on the need for their strength in those orientations. So that's something that we want to go ahead and consider for the part position inside the printer. Fillet everything. Well, filleting everything is an important thing when it comes to printing, simply to reduce stress. This is the most simple example I could model up in SOLIDWORKS just to show you on screen. But I think everybody is pretty clear that's in engineering in any form that rounded corners are better than sharp corners. Now, we try to defeature our parts in some cases in the CAD system, but defeaturing mostly is there for large-scale things, very complex parts, very large assemblies. And the ability to take off fillets from those parts is important to take the stress off of your video card. But it's quite the opposite when it comes to 3D printing. We want the part that's at the detail level, the final production level, to have all the features necessary, which are going to be things like these fillets and rounds. But in printing, it also takes these radius corners and it will layer those parts, materials on top of each other. And in that case, have a nice gradual overlap. Of course, if you had horizontal layered materials here, you're not only going to end up with a sharp fracture point, but you're going to have a layer that just wants to delaminate directly at that point. Absolute guarantee. So fillets are important. Now, they may not be on your part for your final part, but if you're going to 3D print it, it might behoove you to put them either strategically or everywhere, just in order to ease the print process when FDM is a critical feature. So what I want to do is pull up a little part that we use in training and reacquaint a lot of you with a tool in SOLIDWORKS called the Fillet Expert. The Fillet Expert is a nifty little function. It's actually one of those hidden features that we've really revealed to the user a little bit more readily based on the way that our menu structure now functions. And what it does is it gives you suggestions of other things that you might want to fillet in an effort to minimize the amount of selection you'd need to do. So if I go ahead and hit my fillet tool right here, what I'm going to do with it is just simply set up a run-of-the-mill fillet. So we'll go ahead and grab fillet. we'll go ahead and use just a simple 1mm here. And as SOLIDWORKS commonly does, when you select an edge, it'll tangent propagate. But we also give you this selection toolbar that pops up. And if you hover over this, it's going to give you some previews of other selection criteria that are somewhat similar or adjacent to what you've selected. And by hovering over those, you'll get a tooltip and a preview. So this is going to automatically select, based on the edge I picked, all of the other internal loops, which are loops that are similar to the one that I've created, as well as the inside edge of the boss in the middle. If you hover over another one, it's going to get both sides of the loop of the face of the edge that I've just selected. This one here is going to get even more loops, but as you see these, you'll get all convex angles, all concave, and then eventually here, every single edge of the part, which would even do all the edges at the inside of the spline shaft. So that one's more than I actually need. So by backing this up just a little, just a little bit, we're going to go ahead and select just the edges that are right there on the inside of those bosses. Now by clicking this, it'll automatically append my selection tool, and in this case with one selection it gave me 24 additional selected edges, which is phenomenal. Now if I continue this process, say I go ahead and grab a tiny edge right here, it's a little vertical edge. But when I grab that edge, it gives me similar edges here. So do I want the rest of the edges of that boss? Do I want all of the tiny little edges vertical, if you can see the magenta highlighting? Or do I want all interior or exterior edges? Now again, if you go ahead and select the whole smash here, that's going to give you a tremendous amount of selection. In this case, 266 additional edges. I've clicked the part 3 times, and I'm now filleting 291 edges. Say OK to that, and then that will simply apply the 1mm fillet to all selected edges. We'll highlight the part there, and you can see exactly what we're getting. So it really is amazing what you can do just by using a tool like the Fillet Expert and not ignoring that little pop-up menu that actually shows up there. It will enable you to choose things similar, but you have a lot of flexibility with it as well. So we're trying to layer on fast modeling, but really let you still be in control of the ship as far as what actually gets changed. So the last thing I want to talk about here is something I've titled the Silver Platter. And I got this topic here simply because I went down and asked the support technicians for our 3D printing business what they actually deal with on a day-to-day basis. And one of the things that Robert really wanted me to talk about was sending in print-ready files. Do yourself a favor. If you want good quality prints and you're outsourcing these, please set them up for success. What this is going to do is provide them with a document where they don't have to think about where it's going to go into the printer, especially if you've had a conversation with them prior to this about what printer is going to be used. If you put the part in orientation, it's going to be a non-decision as far as the technician's concerned, and there won't be any follow-ups. And if you're printing in a Polyjet, so multi-material, which means material selection is also a potential option, well, send them a multi-body part and then tell them or designate using materials in SOLIDWORKS which bodies are going to be printed in which materials. Because keep in mind, when you're printing on a Polyjet, generally you're printing the entire part in a single print job, and it's digitally blending these layer by layer. So we're not printing a bunch of separate materials and then snapping them together. They are being printed as one cohesive unit. He has the opportunity ahead of time to go ahead and designate which bodies are which up front. So let me show you this a little bit, and prior to that I'm just going to say, Robert, thanks you. When we're looking at something like this, this is a part that I'm going to go ahead and produce here in our Connex machine, probably over the winter here, be ready for summer. That's this Rapala model that I produced. Now I'm looking at this model right now here, and it happens to be in real view graphics. So you can see this wonderful knurling that I have there actually wasn't real knurling. That's something I'll talk about here in just a second. What I do have though is I have a part, and this part, if made out of solid Polyjet materials, I did a study up front where I just simply took one of those 3D printed USB drives that we have minus the electronics, and I threw it in a glass of water, and very quickly realized that that part and that material sinks like a stone. Absolutely no buoyancy. So not only did I have a situation here where I wanted to print my part out of multiple materials, which in this particular case, the body of my part would be more of a gray or white material, and then the spoon here, which is going to be on any Rapala, will be absolutely clear. That to me indicated that I needed to use multi-materials. But my biggest problem happened to be interior to this. Because this material would sink, I also had to go ahead and model in some buoyancy chambers. You see those on the inside, and those are hollows inside my part. If I was to print this part solid using Polyjet, what it will do is it will fill those hollows with support material. So I'll have a waxy buildup on the inside. Now, one consideration you can do is to build your part so that that support material can actually be removed. So this is really a threefold. This is provide your technician with a file that's in body position and multi-body for material designation, but also in such a way that you can also extract the support material effectively. So what I did on this particular part is I went ahead and did a split feature. That split feature left me with a few solid bodies. We've got my spoon, and then I've got my part split into two bodies. And that way, when I go ahead and use my Move Bodies tool, I don't have my part checked out of PDM, my apologies. When I go ahead and use my Move Bodies tool and I open up what this cavity looks like, what you'll see is the fact that I've built in these air chambers. And those are going to need to be there because they're above center line and there's enough air to offset the actual mass of my plastic during a buoyancy study. So in this particular case, I've now moved those to a position where you can see the internal. For Robert's purposes, what I would do is just a little bit more. Is I would go ahead and take my part and maybe move these bodies out just a little bit more. And then in this particular case, maybe go one more step. Take these bodies and just rotate them. So here we'll rotate that over 90 degrees. That looks pretty good. And then we'll rotate this one 90. So what I want is matte side finish down. I want glossy side up. And I want that support material to be able to be removed quite easily from my part. The spoon, on the other hand, well, that one's going to have to wait till a separate print, simply because this particular part would have to have more of my white and black material, and I can't put a third material in there of my clear, so we would get rid of that for now. But those would be parts that if I saved them out as STL or gave them a native SOLIDWORKS file, would be sitting in the proper position so that they would be touching the build plate with support material hitting the proper side of my component. Now, these weren't on the agenda, but just based on the fact that we still have a couple of minutes to go here, what I'm going to do is just talk about a couple of additional tools that are enhancements to what I believe is really going to push 3D printing over the next 5 years or so. And these came into SOLIDWORKS in the last 3 years. So in SOLIDWORKS 2019, we have a new feature that we've added that's called 3D textures. Now, 3D textures are pretty interesting because basically what you're talking about is putting an image in grayscale on a part. So this is just an appearance that we use in SOLIDWORKS. And then what we do is we simply bump that up to different levels based on the contrast and the grayscale. And what you're seeing over there is a part off to the right-hand side. Well, I did this whole presentation in 2018 because I wasn't necessarily going to go here. But what I did during my 2019 prep and showing how this particular feature works is I went ahead and immediately printed that just because I wanted to see what it looked like. And what we ended up with is a part that actually has full textures and actually was produced just by bump mapping this material image, not through traditional extrudes or other types of features in SOLIDWORKS. So it really enables a very incredible addition and enhancement to the way that you can do knurling and these types of patterns directly on parts that are going to be 3D printed. This is also going to push me to maybe go ahead and tweak that Rapala just a little bit. And instead of just having graphics that are showing what looks like scales, I'm instead going to go ahead and actually go ahead and use the textures to create the bump map and then maybe scale over that to create the texture depth overlay. So that's some of the things that you can do just by using some new features that were added into the SOLIDWORKS CAD modeler. Now, another thing that I talk about these days when we're dealing with 3D printing conversations is really simply the fact that we have different ways of designing our parts so that they will be more manufacturable and in some cases more organic based on the way that they were designed. And this is a feature that we have called Topology Study. This was put in SOLIDWORKS Simulation Professional a couple of years ago. And what it enables us to do is set up that hinge bracket that I had there for the hood in a simulation to where our pivot arm is held, we're putting a force on the outside hole, and then we tell it to remove as much material as we desire. Well, the simulation basically goes through and gives you a lattice work of what material must remain. Now, once you have this, you can save that off as a body, as is, and it becomes a smooth mesh, which I then went ahead and printed on my 3D printer there, of course, because I needed to see that this mesh, when printed, was actually really rigid, because my eyes were not telling me that. So what I went ahead and did in that case is went ahead and printed this particular part out. And one last time, we'll pull up the webcam here for a second, because this is the part itself. Now, I really needed to see that the simulation was telling me what it was purporting to tell me, because when I look at a part that looks like this, what I've got is a part that's got a lot more material to it. And obviously the lattice work there looks like a very flimsy part compared to it. But when you look at the part and the way it was actually simulated, held in this hole and then torqued in this direction, of course the solid part is incredibly rigid. But when I picked this part up off the printer and did the same thing, there's almost no flex in that position and direction at all. It really is an incredible result to something that I really just needed to see to believe. So topology study in my case is a better design method, or what's really going to be getting into more of a simulation-based design method that we're going to move forward to as we get further and further into the capabilities of these metal printers. Because frankly, parts are going to be designed like this, and instead of using this as more of a prompter to change your geometry appropriately, they're just going to become the end-use parts. And when I can take a part like this and go directly to a metal printer, that's going to be a very attractive looking organic part as well as a very functional part. So we're really going to bridge those two gaps in the next few years here with those. So what we went over again were general methods, how you decide what you're going to do. And again, these have to really all be considered in one type of a thought, not as an individual one then the other type of an order. So we really need to know what we're going to do with the part and what type of material we need to make the part out of, because what we're going to do with it really determines right up front what type of material you got to make it out of, brittle or strong. Do we hollow our parts or not? Well, really this is a choice that's up to you when it comes to form, fit, or function. But in this case, your print settings and when you see what your previews are going to tell you what your material utilization is. And in some cases, that's the overlining structure. What these really come down to, though, is, do I have what I need for the part? Do I consider building a part because I'm going to print it as 3D as the final part or as just a test bed between there and create geometry as such? And then orientation is definitely going to affect both surface quality as well as strength when it comes to stranded or layered types of materials, which many of them are. Round your edges, please do it. It's not going to hurt you in any way, shape, or form. It won't slow your print down. It won't do anything to that negative effect. It's only going to strengthen things and make transitions from edges to edges much more gradual. And then print-ready files to your technicians. They will thank you and give you quicker turnaround because they won't have to make any decisions. Now, we have a 3D print lab. I don't know if you knew this, but we've had this in our Pontiac office here for the last few years. So if you don't have access, or if you're just wanting to see what these print technologies can do, maybe to make a proper decision on how you need to get your parts built, or how you want to invest in your own 3D printing, come and visit us in Pontiac. We're right in the middle of the downtown wide track loop, and we've got FDM and Polyjet machines running constantly, so you can come and see how they work. Maybe we'll even have some parts there for you to clean. So please do stop by and see us. So with all that said, I want to thank everybody for spending just shy of an hour with us today. I'm going to go ahead and do a little post-processing on our video, and we'll get that up on our YouTube channel. So if you'd like to watch this again, or if you have a colleague who couldn't make it to us today, then they'll have a chance to go ahead and watch it on their own pace. So thank you very much for attending today. I do appreciate it. Please get a hold of us if you do have any questions. My name is Darin again, so Darin at decide-solutions.com, and you can reach most of us at Decide just by using our first names there. But hit our webpage and you'll give a full directory of the team, so you can get a hold of anybody that you like.